Before I begin, I just want to acknowledge that today is the 35th anniversary of the massacre of women at the École Polytechnique. So I think that's on our minds today. I know there's a bunch of ceremonies around the city for it, and there will be the lights that were turned on, I think, at Place Ville-Marie. So with that in our thoughts, we have our talk today. Without further ado, I'll introduce our speaker, who is Leonid Rvbnikov, who joined the UDM this year. So he was at Moscow. He did his PhD at Moscow State University in 2006 on certain algebras related, certain quantized algebras related to Poisson algebras. He was then at the Institute for Information Transmission Problems in Moscow for 12 years before leaving Russia and moving to Harvard and MIT for a couple of years and finally joining us at UDM this year. And we feel tremendously fortunate to have you, Leonid, since your work is on all kinds of interesting aspects of representation theory and algebraic geometry and combinatorics, and you work with Joel, and you've done stuff that I'm interested in. And so we're very happy that you've come and joined us in the Montreal mathematics community. You're going to tell us about tensor invariants of SL2 and arc diagrams. So please join me in giving a warm welcome to Leonid.
Yeah. Thank you very much for introducing and for inviting me to give a talk. Okay, so I'll speak about something which starts from very classical subjects and then surprisingly relates to some very non-trivial combinatorics. Okay, so let me start with classical invariant theory. Suppose I have two-dimensional space over complex numbers. It is acted on by the group SL2. And let's ask the question, what are the tensor invariants of this action? Namely, we can take any tensor power of this two-dimensional space and look for invariant tensor in this tensor power. For example, if we have just tensor squared, there is the only invariant up to proportionality, which is the skew symmetric pairing preserved by the SL2, because SL2 is the same as SP2. It is the symplectic group preserved. Okay, so the next, if we take bigger number of tensor factors, then there are no invariants if the number of factors is odd, because, for example, because of minus unity matrix from SL2 acts by minus one on everything, so there are no invariants. And on the other hand, if the number of factors is even, then we can split the tensor factors into pairs, and for any pair, take this invariant and multiply them. So for any such splitting, we have an invariant. Of course, these invariants are not independent. There are some relations between them. For example, in the fourth tensor power, we have the Klucker relation, which basically says that the fourth wedge power of C2 is 0. So we have this. This means that, yeah, we can picture this as follows. So we can, to any factor, to any of the factors, we can put a correspondence of point on the circle, and to the skew symmetric pairing, we put a chord connecting two points on the circle. So to any such diagram, we put a correspondence on an invariant, and now the Klucker relation is this. So using this Klucker relation, we can get rid of any intersection in the chord path. Subsequently, applying this relation, we see that the space of invariance is spanned by diagrams with no intersecting chords. The number of such diagrams is the Catalan number. It's given by this formula. On the other hand, it is from this, it is still not obvious that these guys are linearly independent. So this is actually the case, but it is not obvious from this. And now to see this, in fact, there are several ways of how to see that they are independent. And let me give the most straightforward one. Namely, I will split the space of invariants in the 2n tensor power into the direct sum of lines using the representation theory of SL2. Namely, so what I will be doing, I will subsequently decompose this tensor product into the direct sum of reducible representations of SL2 and see what happens. So for this, I need some description of reducible representations of SL2. So what is general about this? SL2 is a semi-simple complex Lie group. So the category of its finite dimensional representations is semi-simple. So everything is split into direct sum of reducibles. And the list of reducibles is the following. For to any non-negative integer, we assign an irreducible representation L of lambda, that is the representation with the highest weight lambda, which is the following. For lambda 0, this is the trivial representation. For lambda equals 1, this is the tautological C2 from which we started. And in general, L of lambda is the lambda's symmetric power of the tautological representation. That is the linear span of monomials in X and Y of total degree lambda, on which the group SL2 acts by linear transformations of X and Y. Every finite dimensional representation, in particular this finite dimensional representation of SL2, splits into the direct sum of several L of lambda. And what we are interested in, we're interested in all the occurrences of L of 0 in this tensor factor, in this tensor product. Now, the next what we need is the tensor product rule. So if we tensor two irreducible representations of SL2, this is no longer irreducible, so it splits into the direct sum of irreducibles, and this is the rule how it splits. In particular, if we multiply anything by the tautological representation C2 by L of 1, then, well, if lambda is 0, it is just L of 1, but otherwise it is the direct sum of 2, L of lambda minus 1 and L of lambda plus 1. Okay, so now we can iterate this rule and decompose the 2nth power of L of 1 into reducibles and see what is the multiplicity of L of 0 in this tensor product. So from this rule, it is seen that the occurrences of L of 0, when you subsequently apply this tensor product rule, is indexed by Dick paths of length 2n. Namely, what is Dick path? So you start from L of 0, then you multiply it by L of 1, so you are here. After that, you multiply L of 1 by L of 1. You have two sums, L of 0 and L of 2. And you continue this. So you want to count all the occurrences of this, again, of L of 0. And they correspond to all the paths. The number of such paths is the Catalan number. So indeed, we see that the dimension of invariance is the Catalan. And moreover, we get not only the dimension, but also some splitting of this space of invariance into one-dimensional subspaces, into the direct sum of one-dimensional subspaces. You see, of course, this is a very good splitting into one-dimensional subspace, but it is the splitting is not unique. It depends on some choices I made because for this procedure I took some particular order on the tensor factors. First I did this, and also I took some particular bracketing of the tensor product. So the way of how I in what order I decompose this tensor product. If I took other order bracketing, I will get some other splitting of the space into one-dimensionals and some other combinatorial indexing of the summons. And we can describe this as well. So if I take other order bracketing, then what I get is the following. The ordered bracketing can be encoded by binary tree with an ordering on leaves. So now how to encode what happens when I decompose tensor product of something in the brackets. So here I have L1 and L1. I multiply them, and I should take one of the summons in the decomposition of this tensor product. For example, if I take L of 2, so there is L of 0 and L of 2. If I took L of 2, then I have to multiply it by L of 1 and take the decomposition. For example, I can choose in this decomposition L of 3. Now, on this part as well, I can take some particular summon in the position of this, for example, L of 2, some particular summon in the position of this, for example, L of 0. Then there is no choice. I take L of 1, and then I multiply L of 2 by L of 1. And to have an invariant, I have to take L of 3 from this tensor product. So finally, if I chose this this way of ordering vectors and bracketing the tensor product, I have some combinatorial indexing related to this particular binary tree of one-dimensional summons in the invariant space. So, moreover, it is possible to axiomatize what I have. So what is this combinatorial datum indexing one-dimensional subspaces? Namely, it is labeling the edges of the trees by integers in such a way that all the edges go into the leaves are labeled by 1.
What is the meaning of the blue numbers in the very top?
The blue numbers is just some permutations of the permutation of the tensor factor. So I have some original tensor product, which I just ordered from 1 to n. But after that, I could permute the factors in any possible way and put the brackets. Yeah, and to this datum, I put a correspondence splitting of the space of invariants. Yeah, so I have some. So the combinatorial datum is as follows. I label the tree is fixed. I label all the edges by some integers in such a way that the edges going to the leaves are labeled by 1s. And at any inner vertex, I have the triangle inequality. Triangle inequality and plus the sum of the labels of 3 edges meeting at the vertex should be even, because otherwise it is not compatible with the tensor product. Okay, so So that is. So now the main question I will be discussing that we have some different splitting indexed by different combinatorial data, and the question is how are these data related to each other? And of course there are several possible ways to answer this question, but my way of answering is that there is some natural family of such splittings depending on several continuous parameters. So there is a continuous family of bases in the space of invariants, interpolating between all this, such that there are actually many natural bijections between the indexing data for those splittings coming from the monodromy over the parameter space. I will describe it. So natural here means that these bases in the space of invariants come from some eigenproblems in quantum integrable systems, and I will just now I will describe the integrable systems arising here. So first, maybe before describing integrable systems, let me notice that the basis responsible for the splitting of space of invariants in one dimensional corresponding to a planar binary tree can be regarded as a splitting into joint eigenspaces for some collection of pairwise commuting linear operators acting on this space. Namely, let me fix a binary rooted. Let me fix a binary tree. Then for any inner vertex in this tree, to any inner vertex, I can assign this operator on the 2n tensor power of C2, being just sum of transpositions of tensor factors corresponding for any given inner vertex and any pair of leaves that are descendant of this particular inner vertex. All these operators pairwise commute, and moreover, they preserve the splitting I described. And moreover, their joint eigenspaces are all one-dimensional. So in fact, the above splitting is uniquely determined by this set of pairwise commuting operators on the space of invariants. Now the idea is to interpolate this space of commuting operators. Namely, I can consider the linear for any binary tree. I can consider the linear span of these operators and interpolate this linear span. So introduce some natural family of spaces of commuting operators acting on my space. Okay. And now, what does the interpolation look like? Consider so to any collection of pairwise different complex numbers, Z1, Z2, N, we can assign this linear combination of transpositions of tensor factors. Well, it is not obvious from from the definition, but it is a straightforward check that all these operators for a given choice of the i's, all these operators pairwise commute. And moreover, their linear span as operators acting on the invariant space doesn't change under simultaneous linear fractional transformations of the zi's. So in fact, the linear span of these operators depends on a point depend on this collection up to PGL2 action, up to simultaneous PGL2 action on all these E. And this is the space, the C2n minus the diagonal quotient by PGL2 action is the space or is the modular space of stable rational curves with two n-marked points, with the zi's being the coordinates of the marked points. So to any point of this modular space, I can assign some space of pairwise commuting operators in my invariant space, and potentially the solution to a joint eigen problem for this commuting operator will give the desired family of continuous family of bases. So now to include in this family the operators and the bases I previously considered, we have to extend this this family of commutative subspaces of operators to some compactification of this modular space of curves. Namely, there is the fact it was first observed by Aguirre, Felder, and Wieselov almost 20 years ago, that this family of spaces of commuting operators extends to the Deligne-Mumford compactification of the modular space of curves. So what is the Deligne-Mumford compactification? So I can so what I consider is the space. So what I am compactifying is the space of configurations of several points on the projective line P1 modulo the automorphism of P1. And I assume from the very beginning that all the points are pairwise deep. Now I want to compactify this. So to compactify this, I need to explain what happens when several points get together. And the main idea here in the Deligne-Mumford compactification that the points don't really want to get together. So they do their best to not get together. For example, if we have just 3 points, then our modular space is just a point, and the points say well up to the automorphisms we are just 0, 1, and infinity, and we don't move. We don't get together. Okay, when there are 4 points, it is impossible because there is a continuous invariant which is a cross ratio, and cross ratio can get to 0, for example, or to 1, to infinity. This means that 2 of the four points can get together. But we can look at this picture in 2 different ways. So one way is okay. From the perspective of these 2 points, they say, okay, we stay aside of this, and we see 2 points getting together, but we don't want to have anything to this. But from the perspective of these 2 points, they say, well, we are 1 and 0, and these 2 points go to infinity together from our perspective. Studying compactification, we in fact keep this double data from the perspective of these 2 points and from the perspective of these 2. And what we get in the limit is, okay, these 2 points of Q are in the limit, they are no longer compatible. So each pair of the points sits on its own components, which are connected at a double point, at a nodal point. Okay. And in general, this is the same, and we can iterate this procedure. So what we get is some compact space, and it is a smooth compact complex manifold, parameterizing all possible nodal curves of genus 0 with the same number of marked points, such that on any component there is at least 3 distinguished points which are either marked or nodal, because we want stable, want to classify stable curves. So this space is naturally stratified by the combinatorial type of the curve, which is just the tree formed by the components of this curve. And the deepest strata correspond to binary trees. These are the case when each of the components has exactly 3 distinguished points. Now the main theorem is that this family, so this is basically due to Girifelder and Veselov, that the family of spaces of commuting operators extends to the Deligne-Markov compactification, then to any vertex corresponding to a binary tree, the space of commuting operator corresponding to the 0-dimensional stratum is the span of the above operators corresponding to inner vertices of the tree. Next, for all values of the parameters, the operators from this space act with a cyclic vector. That means that once we know that all the operators from the space are semi-simple, they act without multiplicity, without joint multiplicity. So there is a unique decomposition into one-dimensional subspaces preserved by these operators. And on the other hand, this space is not, these operators are not always semi-simple. There are some counterexamples, but there is some condition on the curve that ensures that this is semi-simple. Namely, if the parameter is real, then all these operators are self-adjoint with respect to some Hermitian form, and hence they are semi-simple. And so there is a unique splitting of the space of invariants compatible with these operators. So we have some family of bases parameterized by elements of the real Deligne-Markov compactification of stable real rational curves with marked points, interpolating between all the bases I constructed. So here comes the monodromy problem. Of course, we have this family of bases, and we can regard it as a cover, as a CN element, CN div covering over the real Deligne-Mumford compactification. So the monodromy of this covering should come from some natural bijection between the combinatorial data related to dig paths or to tree or to label trees or something like that. So the question is what are these bijections in terms of the combinatorics? So more precisely, this is a covering which is S to N equivariant. So there is a natural action of the S to N equivariant fundamental group of this thing on the combinatorial data I described. So the question is what is this? What is this combinatorial group? Yeah. So now a bit about the fundamental group. So I can at least describe some generators of the fundamental group. It can be described as follows. So I can choose as a base point some generic point in the Deligne-Mumford equation. That is just some RP1 with just actual RP1 with several marked points. Yeah, and consider the shortest paths connecting this curve and its image under some action of some permutations of permutation of the marked points intersects the co-dimension 1 strata transversely. So the path, the generators are the following paths. I degenerate this curve to two-component one, and then undegenerate it back to some non-degenerate one, but with the different order of the marked points. So this happens because well, I can do this because each component is in the Deligne-Mumford compactification. Each component is taken up to the action of the automorphisms of P1, which can change the order of the marked points to the opposite. So I can where 1, 2, 3, 4 have gone. Oops. I'm sorry. So this is 1. This is 2. This is 3. This is 4. I'm sorry. So this is like on the clock. So this is après-midi. Yeah. I'm sorry. Yeah. So this is the same. I didn't do anything with this component, but I did something with this component. Yeah. So these are the generators. So that is to any interval in the cyclic order of points. I can put it in correspondence and a generator of this group, which is an involution, and satisfies these two conditions. Yeah, so this is relatively easy to see from the topology of Deligne-Mumford compactification. There are also some additional relations, but maybe not so easy to write down explicitly. Okay. And now to compute this monodromy, I need to know something about the eigenbasis about the joint eigenbasis for the commuting operators. And by the way, how much? So the eigen problem is solved by so-called Bethe ansatz method, which is something frequently used in quantum integrable systems. So in this particular situation, the idea of Bethe ansatz is to look for the eigenvectors in some particular form. Namely, I take the highest vector in this tensor product, which is the product of x in each of the in each of the two-dimensional spaces, and apply to this highest vector some lowering operator, which reduces the degree from total degree n to 0. So this lowering operator is a linear combination of lowering operators in each of the tensor factors. This is the generator f of SL2 of the Lie algebra SL2 acting from x to y and sending y to 0. So I sum this up over all the components, and now the main theorem here is the following: that such vector is a joint eigenvector for all the commuting Hamiltonians of the Godin integrable systems, if and only if these Bethe ansatz equations are satisfied. And moreover, if they are satisfied, then this vector is SL2 invariant. So it belongs to the invariant. And moreover, such vectors, at least for generic values of the parameters Zi, such vectors form an eigenbasis. Okay, so now how to interpret this Bethe ansatz equation? So we can encode the solutions of Bethe ansatz equations in the following way. So to any collection of these auxiliary parameters uj, we put in correspondence the second order differential operator of this form. And it is to see that this differential operator may have singularities at the points Zi and uj for all j, but the leading polar term at the second order pole at all the points uj is 0.
What do you mean the singularity of an operator?
No, it's a singularity. I mean the corresponding differential equation. Just the well, if I write it in this form, then the singularities are the poles of this function. So this function is given by Muir transformation. And once A of u is this, it has a pole of degree not greater than 1 at the points uj, and Bethe ansatz equations are precisely the condition that this guy has no pole at uj for any j. So what I have here is the coefficient of q at the first order polar term at Qj. And moreover, the eigenvalue of the codent Hamiltonians on Bethe ansatz vectors are precisely these numbers Qis. So if I decompose, if I expand Q of Q in at the point Zi, then the highest order polar coefficient is fixed, and the next coefficient is responsible for the eigenvalue of the Hamilton. So now I want to say that such well, this means that this if all the Zi's are real, then these coefficients are also real, because these are eigenvalues of some Hermitian self-adjoint operators. And this is, as I understand, the particular case of Shapiro-Shapiro conjecture. Yes, so it is defined over reals. And now I want to interpret this. So far we interpreted solutions to Bethe ansatz equations, which are one-to-one to the eigenvectors for joint eigenvectors for the commuting Hamiltonians. We identified them with Fuchsian differential operators of this form. And now I want to interpret these operators as projective structures. Once I have such an operator, locally, the corresponding differential equation has two solutions. It has two solutions, and I can take the ratio of them. And it is a local mesh from P1 to P1. That is a projective structure. And moreover, if everything was real, then this projective structure is compatible with the real structure. So it is a real projective structure on the real project, with some singularities at the point Zi. So moreover, since my operator has this form, this psi of u is in fact globally. So it is a function. It is indeed a function. It is not a local section of something, but it is some global. And moreover, the I's are the critical points of psi. Moreover, the I's are not only critical points, but they are simple critical. Next, it is possible to extend this description of the eigenvectors to the Deligne-Mumford complication. So for this, so if my collection of points Z1, Z2n is no longer just a collection point of a single P1, but nodal curve with marked points, I still can say almost the same. So I could, that is, I can determine what happens to the differential operator when we degenerate the curve, and what happens to the projective structure. Namely, I have on each of the components, I have a projective structure which has a singularity at the nodal point, such that the singularities are compatible for the components meeting at the nodal point. So now why I'm doing all this? Because I can see some combinatorics from this projective structure. So from now on, I assume that my points, marked points Ci, are real. So I am living on the Deligne-Mumford complication of the space of modular space of real stable rational curves with marked points, then the map psi is defined over R. And this means that the preimage of the real projective line is something uniquely determined. Moreover, it is some collection of curves on the Riemann sphere, which is symmetric with respect to, which is preserved by complex conjugation. And moreover, this preimage has some self-intersections, and these self-intersections are possible only at the points zi, which are real points. So this means that on any hemisphere we have a picture like this. So I can draw it. So we have a sphere. We have the point zi sitting on the equator, which is RP1. And this preimage is some curve which contains, of course, this, but also some other components which are symmetric, which are with respect to the complex conjugate, which are preserved by complex conjugate, something like that. So this means that on any hemisphere that we have the two symmetric pictures on both the spheres, and on each of them we have so-called arc diagram. So some collection of non-intersecting arcs connecting the points zi on the disk. So the idea of constructing the pictures like this from projective structures, as I understand it, goes back to Thurston. So our small contribution was that we can extend this to nodal curves. So all the nodal curves can be obtained from the non-degenerate ones by pinching this disk at several points. So finally we get this. So we get an arc diagram on any of the disks corresponding to the components of the nodal curves, which agree at the nodal point. That is, the number of arcs ending at the nodal point here is the same as the number of arcs ending at the same nodal point. And for the marked point, the number of arcs should be 1. In fact, you can generalize this construction from the representation theory to make the marked points more complicated to allow multiple arcs from the marked points as well. But for now, so this means that that for any point in the parameter space, the joint eigenbasis for the commuting operators is naturally indexed by pictures like this. And this is so for both for non-degenerate curve, for degenerate curve, for any nodal curve. And now, so in particular, this is the example of the most degenerate nodal curve, which has exactly 3 distinguished points on each of the components. So the base, so all the pictures like this on this particular curve correspond to basis vectors in the invariants in this tensor product coming from this tree. And the markings of edges of the tree correspond to nodal points, nodal or marked points, and the labeling corresponds to the number of arcs passing through the nodal point. So this is how they are related. Okay, now so combinatorially this is the same, but we can regard this as a special case of arc diagrams, which is more general. And in terms of arc diagrams, we can describe the monodromy of the bases along the parameter space, namely the action of my generator of the cactus group of the fundamental group of the real Dillon-Mumford space is just just more or less by definition. You do the same procedure with the, but not with the real curve, but with the disk side, and with the arc diagram drawn on the disk. So the combinatorial rule is that you pinch this disk and flip one of the components, and then unpitch back. And this completely describes the monodromy group. Very complimentary. Okay, this is so maybe that's all. Thank you very much.
Questions for a speaker?
Any questions? So is there any high dimensional version of this? Like if you start with the SO2, you start with SO3.
Yes and no. So of course, the representation theoretic problem is very general. You can replace SL2 with any semi-simple Lie group, and you still have the Godin, and in fact you can replace C2 with any collection of finite dimensional representations of the Lie group, and you still have the integrable system. This is of the same sort, and you have similar Bethe ansatz equations. They're more complicated, but still this is a similar form. And moreover, it is possible to describe solutions of Bethe ansatz equations in terms of something like differential operators. So for GLN, if you replace SL2 by SLN, then you just replace second order differential operator with an nth order differential operator, and which is decomposed in split in the product of first order differential operators with singularities at several points. And there is a notion of so-called opera, generalizing this to any semi-simple. On the other hand, it is actually we have the same bunch of theorems stating that the joint spectrum of commuting operators coming from Godin model is simple for any real values of the parameters. So there is a well-defined monodromy problem over the same space. But there is no description of the monodromy like this. There is, at least I don't know anything generalizing arc diagrams to something to anything outside SL2. We have so together with Joel and Eva Khalasheva and Alex Weeks, we have different description of monodromy. That is also combinatorial, but it is in very different terms. In terms of Kashivara crystals that are combinatorial models of representations of the Lie group. As far as I know, even for SL3, there are no pictures like that.
Well, eventually for SL3, you have a basis invariance given by the webs.
Web diagrams, but can you put them on the projective projective line to make them move and transform under degenerations? And is it?
No, it's not. I don't think it's no.
I don't know. I mean, also there's other variants in this where instead of getting maps from P1 to P1, you have maps from P1 into P2, and then also it's not clear how to draw that.
In fact, the maps responsible for this are the maps from P1 to the flag to the flag array, to the complete flag array, the full flag array, and it is going to be more complicated. It's longer, no longer a map from something one-dimensional to something one-dimensional, something more general.
Second question. So the SU2 invariant form that the Bethe Hamiltonian is preserved when the parameters are all real.
Yeah.
This is maybe the part. So I know some parts of this story previously, but I was curious. Like, do you know anything? Do you know enough about it to say what happens if you take some of the parameters to be complex conjugate pairs instead of real?
Yeah, we have some partial results actually. when there is a one pair of complex conjugate, and all the others are still real. Then there is. It is not always Hermitian, but you can put some reasonable conditions on the highest weight to make it. But outside this case, I don't know anything, and I am not optimistic.
Questions? Okay, let's thank our speaker again. The reception upstairs with wine and cheese in the south lobby. So we'll see you all up there.